Welcome to Chapter 2, Unit Cell Calculations. In this chapter, we will go inside the lattice and look at the atoms that are placed in the unit cell. The chapter objectives for Chapter 2 are to calculate and graph fractional coordinates, to manipulate the atoms in the unit cell, to use computer graphics to display the hexamethylbenzene molecule in the unit cell. You will be doing this as your first exercise, but don't worry, you have a video to help, another video to help you out. You're going to be introduced to the metric matrix known as the G matrix, and this allows you to calculate for all non-orthogonal systems such things as interatomic distances, interatomic angles, areas, volumes, and you'll be working in both first 2 dimensions and then 3 dimensions. We will then undertake a detailed calculation with a quartz crystal, and we'll use the P matrix to transform fractional coordinates, the metric matrix in area or volume, area in 2 dimensions, volume in 3. We will go through a detailed calculations with hexamethylbenzene. We'll define crystallographic directions and planes, and finally we will calculate the density. And then also, almost forgot, we will revisit thermal expansion and isothermal compression, only instead of doing linear isothermal expansion like we did in the first chapter, we can now look at it in terms of a volumetric relationship. So let's start out with section 2.2 on fractional coordinates. We have a coordinate vector R, and the coordinate vector has 2 basis vectors. It's a vector on both sides of the equation, and here A and B in 2 dimensions are the basis vectors. Here they are, A and B, and we're going to have introduce the fractional coordinates x and y. To see the fractional coordinates, we can draw lines, these dotted lines parallel to the A and the B. We're actually looking at the projections. Notice we always have to take into consideration that we have a non-orthogonal projection, so our projections will not necessarily be orthogonal. Here is the x projection. So here we have this vector is projected along x here, and you can see that it's just about halfway along, and the y is projected along the b-axis, and that's about 2/3 of the way along. So let's look at an example where we draw the atom A in the AB plane, and it will have fractional coordinates of x equal 1/2 and x equal 2/3, and our cell has lattice parameters equal to 10, A and B are equal to 10 angstroms, and gamma is equal to 120. So in order to find out the fractional coordinates, we simply multiply them up. Here's our fractional coordinate times our the scalar of along the a-axis, and we get our 1/2 and 2/3 translates on a 10 angstrom axis to, each of them are 10 angstroms to 5 and 6.7 angstroms. You can see that in this picture. Here's the A, here's the projection of A along big atom A along the a-axis, and its projects its fractional coordinate is 1/2, and so 1/2 times 10 gives you 5 angstroms, and likewise along here the y is 2/3, so 2/3 times the 10 angstroms along the b-axis gives you the 6.7. However, from now on you really won't have to do this because we're going to have the computer do it for us. Here's the definition of fractional coordinates. They are the atomic coordinates given as fractions of the basis vectors. You will have to know this because we will have we will have definitions on our tests and on our quizzes. The coordinate vector r is specified as using the fractional coordinates. We have, this is a three-dimensional one, of course. We have the basis vectors a, b, and c, and the fractional coordinates x, y, and z. And then again, as before, this point A is indicated as coordinates in angstroms of 5 and 6.7 angstroms, or we could equally refer to the point as in fractional coordinates. The fractional coordinates are unitless, and they would be 1/2 and 2/3. There's a real advantage to using fractional coordinates, which we'll see in this next example. So if we take 5 unit cells and we just keep translating, remember that's the whole idea of having a unit cell, is you can keep translating it. And you can see here integers can be added or subtracted from the fractional coordinates to find the identical atom's location in another unit cell. For example, over here at in cell A, we have, this is our starting cell here with our A and our B. Capital A has got fractional coordinates 1/2 and 2/3. If we look at cell B, that's moving 1 over to the right, we're simply adding 1 along A, so its fractional coordinates would come down over here, so it's 1 on A and then 1/2 on B, 1/2 along this in cell B, so here that gives you 1.5, and our projection along the B-axis is still 6.7. If we go up to cell C, in this case we're traveling along the B direction, so you can see you add the 1 to the B, and in cell D we come over here, not 1 unit cell but 2 unit cells, and all we do is add a 2. So that allows us to very easily calculate different positions. Now let's have a question to ponder. What are the fractional coordinates of atom A in cell E? You do that. Okay, I guess you've gotten it. Here's the answer. It's -1 in A, so it's 0.5 minus 1 gives you -0.5, and then B is the same at 0.67. Let's look at section 2.3, which is plotting atoms in the unit cell. Now we look at our coordinate matrix, which is X, which referred to as X, and it's a column matrix that has the fractional coordinates in it. And now we need the Cartesian transformation matrix, and we can apply that very, very nicely to points within the unit cell as well as to the lattice points. We derived this in chapter 1 for lattice points, and now we can just apply it also to points within the unit cell. So here we're going to plot a single atom. X, Y, Z are the fractional coordinates. So we take the fractional coordinates and we multiply it by the Cartesian coordinate, or rather the Cartesian matrix, which consists of the coordinates, and that'll give us, we saw this in chapter 1, and now we simply multiply it by X, Y, and Z. And now let's look at a single example. A single example would be plotting that same a carbon atom A. That's why I chose the A in hexamethylbenzene. If you look on that chart, it has these coordinates. So here we can have the C matrix. Each molecule, or each crystal I should say, has its own special C matrix because it has its own special A, B, C, alpha, beta, gamma. So you can see here we have that information right here. The C1, C2, and C3 you can look at in chapter 1 and see those are functions of A, B, C, alpha, beta, and gamma. And you can apply, here's the cell constants. you can apply that to the C matrix, and you can see, say, the A is right here. Well, we look A, here's the 9.01, and then we have, say, B cosine gamma. Well, gamma is very close to, close to 120 degrees. The cosine of 120 degrees is minus 1/2, so it's going to be roughly minus 1/2 times B. B is 8.9, and minus 1/2 of it is pretty close to minus 4.4, or so, and that's exactly what it is when you put in the 119 degrees 34 seconds. And likewise, you can see all the rest of these entries into the C matrix will derive from ABC, alpha, beta, gamma. So this allows us to print or make a graphic picture out of, which is a lot of what we're going to be doing. So now we can start out with our fractional coordinates, and we can multiply the C matrix times the fractional coordinates, and that will give us the coordinates that the computer will actually plot. And here's our hexamethylbenzene. Here we have 12 atoms, and we have 12 fractional coordinates. And notice we have capital A through F, so A, B, C, D, E, F. And then we have little a, so little a is opposite A. This is just for this particular crystal that it was so labeled. And the reason it's labeled in this way is you'll notice that little a is the negative of A, so 0.017 goes to minus 0.017, 0.182 goes to minus 0.182. This shows a symmetry operating. We're not actually going to be concerning ourselves with any symmetry, but I'm just showing you how much of a help the symmetry can be, and we'll do this in actually our calculation. I want you to notice also that all the z's are 0, which means that the carbon skeleton, notice we've left out the hydrogen atoms, is planar, and in this particular orientation of the cell, it lies in the plane, in the ABC plane. Okay, so if we plot those points directly from the literature from Professor Lonsdale, we get, here is the ABC all in the unit cell. Notice there are no bonds drawn. The literature will give us the experimental work will allow us to get the positions of the atoms, but the bonds are really to a certain extent, they're what you put in. So it's pretty easy. You look at this particular situation. There are ways of measuring something about the bonds, but roughly speaking, you are really going to be putting in the bonds. So in this particular case, it's pretty easy to see how the bonds would be put in. But that's a very important point. In general, most crystallographic experiments give just the positions of the atoms. They do not actually put the bonds in. Here's our atom A and little a, and you can see how capital A is in the first quadrant, the top quadrant here, and little a is in the negative quadrant, and we can see that these have 2 plus signs on them, and these in effect have they do have 2 minus signs. Okay, so to get all the fractional coordinates of the atoms in the same unit cell, remember we can always add or subtract integers until everything lies between 0 and 1. So here we're going to take atom A, and we're going to move that, we're going to add 1s to X and Y, or to A and B, the two components, the X and the Y component, until we get into the unit cell. So if we add 1 along the a-axis, we come over here, we're not in yet, so if we add 1 in the b-axis, there we are, we're inside the unit cell. And here we are giving the coordinates inside the unit cell. The a, remember, was the minus minus. It's in this negative cell. Here's the negative part of the plane, so here's minus minus. We're adding the 1 1 to it. So here's the addition, and we get points 0.929, and you can see that looks just about right along A. We're almost all the way up to 9, and along B we're pretty close to it too. We're up on the 0.8. So you can see that this is we're translating everything back into the unit cell. When we do it for all the atoms in the unit cell, this is the way the calculation would look. Now, since you don't know what the bonds are, it's really hard to put the bonds in like this. So what you really do in crystallography is you, of course, add the translation of the unit cells. And that's why it's important to be able to do this type of calculation. We've already really explored this in the Escher picture in chapter 1. And here's our unit cell with the fish. And when we look at our unit cell, which contains all the information for creating the pattern, we see how our poor little fish got chopped up. Well, in the same way, the hexamethylbenzene got chopped up too. So let's look at a few things that we've learned so far now. A vector is unchanged if it's translated parallel to itself. Well, you know that from math, so you can and each atom is located at the end of a vector drawn from the origin to the atomic position. So that's how we indicate the atoms. We can add we can add a single set of plus and minuses to all of the fractional coordinates. In other words, if we translate all of the fractional coordinates by the same amount, we're not changing the relative shape. And all of the atoms can be brought into the unit cell, and their relative positions are preserved since the coordinates are really all translated together. Now this is going to come up later. It might be, I think you can see it from that picture. And now we're going to look at the drawing now of the hexamethylbenzene. How we've gotten this is we had the hexamethylbenzene as it came from the literature, so it was centered around the 0, 0. We added a half, so we translated the whole hexamethylbenzene into the center of the cell. That was just fine because you can add the same amount to every, you can translate it by adding the same amount equally to every single atom. And then we connected it because we can see this benzene ring and the methyl groups hanging off the benzene atoms. So the homework is going to be to produce this figure. The starter program, which you have in your in Scholar, it's called Go to Scholar, Chapter 2, then look under Chapter 2, Starter 3 Atoms.m. That will give you your starter program. And when you do that, it's going to give you the first 3 atoms in the hexamethylbenzene system, and then you are going to translate it to the center, and you're going to label it and put the bonds in. This exercise will be extremely useful later in the course. But you're not alone. Look at this poor little lonely polar bear. But that's not you, because you can go to Scholar Resources, Chapter 2, 2015, and you'll find a video that I made, and that is called Chapter 2, Figure 2, and you can't put a dot in there, so it's 2 underline 5, and it's listed as a .swf file. So watch this video, and step by step you'll go through and be able to do the exercise. To remind you what you're really doing is, we'll review this. Here's your coordinate matrix. You're setting your atoms, so you'll have in effect all 12 of your atoms in a single matrix. Then you'll be preparing that matrix to be plotted. So you'll take the C matrix, which converts the fractional coordinates to coordinates that can be plotted. And here's your program. The first part of the program defines your coordinates. Don't forget to put your own date and your own name, and then you're adapting to make figure 2.5. And now you put in, you're going to have your A, B, and C, your alpha, beta, gamma, and now the unit cell is drawn as in chapter 1. That's already in there for you. The next thing you'll be doing, as I've explained in the video, is you'll be looking at the fractional coordinates, which are both in the book and in an earlier slide, and you'll be putting, we were calling them carbon A and carbon B, so then you're going to put all the rest of the atoms in, and then you'll find that you get all of the atoms will look just like this. And now we're going to translate them into the center. This is a little hint which I've actually applied. You don't really have to use this. So all the atoms are moved to the center of the cell by adding a half to each of the fractional coordinates. And here's what the program that I've written for you. It's not a programming course. You can see the conversion has, we're adding a half, so these are the carbon atoms after the half has been added, and then we convert those coordinates to ones that you can plot by multiplying by the conversion, and then we plot each of those terms. So this is what you're going to get, and be sure to watch the video.